We deal with data analysis, or we do community level analysis, or we have a specific data about things. This data can have two structures. It can be discrete data or continuous data. And in our level of analysis on the things that we are using in this class, we will have two types of data. And let's actually write them here. When we do community level analysis, we have discrete data and we have continuous data. Okay, for discrete data, if we have a community, something like this, the discrete data is called features. We use feature data, features. And this one is called rasters, raster data, okay? So features is anything that is discrete data, it's not continuous. Like, for example, if you have buildings, is these buildings continuous? Each building is separate, right? So this is discrete data. So your community has some buildings like this. Blocks, right? These blocks are separate and each one can be represented separately. Like you can have a table and this table have building number 1, building number 2, or building ID 1, 2, 3, up to 4. Each one is separately, and you can do processes on each one separately. So this, for the buildings. Continuous data is continuous, like what? Like if we are dealing with topography, so we are looking at the digital elevation of the ground. So the ground is continuous, right? So it cannot be modeled as a discrete data because the ground is continuous. So we need a raster data of the digital elevations of my study area. So what we have something called raster data. It's basically, if this is my land, so your map will cover your entire land. And this continuous data have resolution. Like you can have your resolution very, very fine, like 1 meter, 0.5 meter, or it can be 100 meter, 200 meter. This is how we get data for hazards. Like if we are looking at flood hazard map, it's in a raster data. Like it tells you what is the flood depths at each location, because the flood depth is continuous. Like when the water doesn't like move like specific bars. It's continuous data. So it tells you what is the flood depths at each location. Same thing, if you have a wind hazard map, it's a raster data. The tsunami hazard map, it's a raster data. A spectral acceleration hazard maps, it tells you what is the spectral acceleration at each location on the ground. So this is also continuous data or raster data. When we deal with this data, it has a resolution like, it's something like this. It's defined by the pixel size. As soon as the pixel size is very, very small, your data will be very, very fine, but the size of this data will be very, very big. So if you are looking at resolution of 1 meter by 1 meter, I expect that maybe if my area is big, my file size, I used to have raster files of 10 gigabytes. Can you imagine just one picture, just an image, has 100 or maybe 10 gigabytes. Why? Because each pixel has data inside it. So each pixel, like for this pixel, it says that the flood depth is 1 meter. For this pixel is 1.1. For this pixel is 0.9. For this pixel is 0.8. So here's what is the play of the pixel size. If your pixel size is very, very big, let's assume it's 100 meter by 100 meter. I will have a problem. Why? If I'm looking at the flood depths and I have 100 meter by 100 meter, you can have 4 buildings in this area. And you will end up with all these buildings has the same flood depths, because this is my pixel size, and my pixel has only one value of the data, 1.1 meter. So when you extract the value of the flood depths at building 1, 2, 3, you will get the same. And this we have with, like I have been working with Mexico Beach, Florida, and I have a wind hazard map. And actually the pixel size that I got from the coastal guys is like 1 kilometer by 1 kilometer. And Mexico Beach actually is 1 kilometer by 1 kilometer. So all the buildings within Mexico Beach was having the same wind speed. Why? Because coastal guys who is doing coastal analysis of the hurricanes, when they model the hurricane, they are modeling the hurricane in the ocean. So they work with very, very big pixel size. And when they transport my wind speed, or they give me their wind speed, they transfer the wind speeds at the same pixel size. It's 1 kilometer by 1 kilometer. It doesn't work. It doesn't make sense. Okay, so this is how the pixel size can play in our models. Okay, so this is for continuous data, and it has a raster data. Let's put some examples. Flood hazard map. By the way, these things are not in the notes, so you guys maybe you need to take pictures or flood hazard maps. When have a raster map that tells you what is the spectral acceleration at each pixel. Okay, for the discrete data, as we know, it's a discrete data. It's a data at a specific building. Can have different shape. Can be points. Can be polygons. Number 3 can be lines. Okay, so as we know, buildings are polygons, right? You can make some lines. Maybe this building is a rectangle, so it has 4 lines, so you'll have this building something like this. So this is polygon. Sometimes we need to deal with building not as a polygons. If we need to do some data analysis, we need to convert this polygon to one single point to make our data less heavy, and we can do processes on these data like Python or MATLAB, so we need to convert these buildings to points. So there is a ways to convert these features. We call the polygons, the points, all discrete data as features. So when I say feature, I mean point, polygon, or lines, okay? Feature is a discrete data. So I want to convert this polygon feature to a point. So there's a way to do this, and I'm gonna teach you how to convert this, okay? So buildings can be represented by polygons or can be represented by points. Okay, how about lines? When we use line feature, what do you think? Like, when can we use line features to model what?
Maybe like a road.
Roads, like road network. If you want to model the road network, since it's linear, we can make a link or a line, and this line has data, has like the start node, the end node, the traffic speed on this link, and also is it one way or two way? Many things you can put a lot of data on this line. Same thing, you can put a lot of data on the point or the polygon. Like you can, in this point, like when I say discrete data or I say feature data, I can put hundreds of data on this point. I can tell that this is a building, this building is residential on a crawl space foundation, is designed or it's built in 1997. For example, it's a 2-bedroom apartment, it's in flood zone 1 or it's in flood zone 2. I can put hundreds of data in this building. Even census data, I can tell how many people like how many people live in this building. Like there's 5 people live in this building. How many children? 2. How many adults? 3. You can put thousands and thousands of data just inside this point. But in pixels, it's only have one value. It's called pixel value. And the pixel value can be 1. This one can be a flood depth, or can have 50. This 50 can be wind speed. So this only can have one value. However, sometimes we can convert discrete data to raster data. And we can convert raster data to discrete data, but this will not make sense. Like when you convert this discrete data, you will convert each pixel size to a single point in the middle, and this point will tell you the flood depths at this point is this, and this point is that. Okay. Weather, it's very important that we know that we can convert discrete data into continuous data. If like we are going to the field, or if we are going to the field to measure the high water marks. So you got a high water marks here and a high water mark here. So when you got the high water marks, is that discrete or continuous? Discrete, because it's at specific locations. You didn't measure that. How does the continuous look like? We need to convert it to continuous. So when we measure high water marks at just a specific location, like at 100 meters from here and there, I can't measure 1,000 of high water marks. I have like only 5 people on my crews, and we plan that we are going to measure high water marks at just a specific location. So you got a high water mark here, there. All this is a discrete at points. So we can use these points and convert them to a continuous data. Why? By using By using like interpolation.
Yeah,
Like you interpolate the value in between this based on the values up, down, and around.
Like a gradient.
Yeah, you make like a grid and then you interpolate to convert them. And this is how we use it sometimes for wind speed. Like you have a measure to measure the wind speed at this location and this location, and then you can make a map to measure what is called grounded truth wind speed, not modeled wind speed. What is the ground measured wind speed look like? So this is just like an overview how the data that we are going to handle look like. So sometimes we will have, when we deal with hazard maps, so we will have discrete data. Actually, there's other things like not hazard map, like if sometimes when we do hydrologic analysis, we need what is called soil map. Because based on the soil type, we know how much water will go deeply infiltrated in the soil. So we need a soil hazard map. So the soil hazard map need to be raster, continuous. Land use, based on the land use, like if this is a forest or soil, or this land use is a residential area, this is agriculture area. So based on the land use, we can know how much infiltration will go. So the infiltration is based on the land use, it's based on the soil, it's based on the digital elevation map. All these are under the raster or the continuous data. But for discrete data, it is just buildings, networks. Like it's not only lines, is not only for transportation. So if you have a water network, so the water network is line, like pipes, and you know how the pipes is going, so this can be lines. Also the transmission or the power network. The power is like you have a transmission towers and you know where is the power is going, and you have poles, and this poles is taking the power from here. So the people that I work with, they model the power network, they use lines, and each line has lots of data. What is the voltage in this line? Where does this line go back and forth? Okay.
Pipelines also.
Anything that is linear, like even the gas network, the sewer network, the telecommunication network, any network or any lifeline is modeled by a line. Buildings, facilities, even. But here's the thing, like when we do power or water, the power network, when we say the power network has links and also has nodes. Like it has the plants, the power plant. This is a node, so you have to identify a lot of things about this node, how much power you are getting from and substations. And maybe you have a solar panels that gets into the system. Same thing, the water network. You have the water treatment plant, water tanks. So all these nodes on your networks. Okay, so this is one of the things that I need to touch base on. So this is the data type. Actually, I was about like to use my laptop and show you guys how we can convert or process this data on ArcGIS, but maybe next time or if we have half a lecture. So I might use half of the lecture or all the lecture next time to see how can we process this data so you get your hands on ArcGIS and do some examples. Does anybody have any questions on the data types? Does anybody have any questions on which stuff is better? This stuff, right?
Yeah.
Me too, that's my favorite. Yeah.
Doctor, I have a question. So the continuing of the class will be like probability
No.
stuff?
So this probability, I'm gonna reduce the content. So moving, maybe the next thing that I'm going to explain is the extreme distributions, and then I introduce fragilities and reliability, maybe like a couple weeks, and then everything will shift to this stuff. I could have made this class just applications, but I didn't want to do this. It will be very good and it will be a very great class. It will be very easy for me. But without this stuff, you can have an idea about when I say this is normally distributed variable, when I say this is a mean and standard deviation, and let's develop fragilities, or this 100-year event, and I tell you this is the probability 0.01, you will not understand me. So that's why we had to do this boring stuff so that we can get some exciting.
Doctor, what about the probabilities that we did before this, the homework one, let's say?
We are not going to use them. Like, okay, this stuff is completely separated from this one. But this one is very important to have the common sense of when I say two random, like for example, when I talk about flood depths and flood duration. This is two correlated things that happen together. So they have covariance and lots of things. So you understand that there's two events that happens that have jointly distributed random variables. So you need to, but when we get to this stuff, it has nothing to do with this part, but it will be very interesting things, right?
And the midterm will include questions from homework 1, which is like proving formulas.
I don't think it will have proofs. It will have like
Applications.
application-like questions. The proofs is just like you go online and search, and it will be open book, so you can write your own formula, but not open internet. Okay, not open ChatGPT. Okay.